So, yeah, I think it's the time and we can start.
Okay.
Welcome everyone to join us. And I'm very honored to have David Louie here. And he's a distinguished technician staff from Sandia National Lab. And he gets his PhD degree and bachelor degree in nuclear engineering from the University of New Mexico. And now he works in the civil accident model and ANSYS department at the Sandia National Lab. Today he will talk about enhancement of the sodium pool fire modeling MELCOR. Let's welcome Dr. David Louie.
Thank you all. Thank you for listening to me on this talk. I'm honored to speak in this seminar at the University of Wisconsin, particularly Professor Wink to invite me to do that. My title of the talk today is on sodium pool fire modeling in MELCOR code. Of course, sodium is the coolant in this sodium fast reactors, and sodium is very reactive metal, so especially contact with air and water. So even at room temperature. So my talk is based on that. So my outline is basically is following. For those of you who doesn't know MELCOR, I'm going to talk about MELCOR and talk about the liquid metal properties in MELCOR that we enable us to model sodium fast reactors. And then I'll talk about the overview of the sodium chemistry models in MELCOR right now. Uh, and then we talk about the collaboration with JAEA under the CNWG framework from DOE. The acronym is showing here, but the footnote you see is what it stands for. And then we talk about the enhancement under the CNWG collaboration for the sodium profile model, the current models in MELCOR. And then we talk about the benchmark against the JEA 7 F7 series pool fire tests, and then do some code to code comparison and finally provide some conclusions. So MELCOR is a non-parameter code. Here saying is an advertisement here as a code for international nuclear safety. And MELCOR is an integrated engineering level 2, system level 2 simulation survival accident, which is developed at Sandia um, more than 30 years ago for starting 30 years ago for U.S. regulatory commissions. And you saw in this diagram here or picture here showing a PWR, typical, severe accident. You have a core melt and in the RCS, and it shows some of this important severe accident phenomena that MELCOR does model, do models, such as the accident initiation, thermohydraulic in the RCS, and loss of core coolant, core melt, fusion product release, vessel failure here and showing this cartoon here, and then transport the fusion product around the RCS, inside the RCS, and also in the containment. And then the core melt, like I said before, and to the floor, concrete interactions. And then you talk about fusion product removal from engine safety features like engine spray and things like that. And then iodine chemistry. That's for light water reactors. Now, currently, we have over about thousands now. This slide is a little old here, showing it's used internationally. We have, like I say, we have over 1,000 licensed MELCO users now. Uh, about about a third is in Asia, and the third in the U.S., and the third in Europe, and then some on the other continent or other regions. And in the U.S. itself, we have quite a bit in the commercial sector, and then of course the universities is a majority part, and then the government, of course. And DOE is about 40 or so, and NRC about 40. DOE mainly applying not only just for nuclear energy, but it's also for DOE um, nuclear facility, like Sandia National Lab, Los Angeles National Lab, etc. And he's showing a map here showing we have an uh, all over the world that use MELCOR, showing some of the countries, and every annually we have a protocol international collaboration severe accident CSOP, and then usually in the summer, early summer, associate in conjunction the MELCOR co-assessment program, MCAP, at the same time. And then in the spring, we have also a European MELCOR user group meeting. And in the fall, usually we have the Asian MELCOR user group meeting, primarily the Japan, South Korea, Taiwan, and China, and then now including Singapore. Hopefully in the future, we might include India. Here, showing you the development cycle here in the last 20 years, 2 decades, from 2000 to 2020. 185, but there's an early versions of 182 and 1.1.8, which is in the starting in the 80s. Just showing here the last 2 centuries. I mean, two decades here. 185 is a start. It's showing here as an official release. Then you can see the number of model development being uh, developed into MELCOR, even from curved lower head, more better simulation, a convective molten pool, and then point kinetic and the smart restart hydrogen production. This is the cogeneration for use for looking at cogeneration of hydrogen. We do have a H2C model. That model uh, uh, sulfur iodine cycle that use conjunction with the high temperature gas reactors. And then you have turbulent deposition, which is important for high velocity that actually deposit on the ducting or piping. And then you have we have also have a magnetic fan cooler as part of the engine safety feature in the containment. Core quench, spreading model, and the core lower head containment model that is in junction with the AP1000, etc. Have improved eutectics and the most important one is vector control function, which is the jewel of a MELCOR, which is a real powerful package that enable us to model explicitly outside using a code modification, give right equation in the input so that we can actually test the models, which I'm going to show in this talk here. Okay, we have resuspension model in the aerosol. The next one is showing the sequence that looking how we changing from beginning of the code the widespread spectrum here, and then 185 written in Fortran 77, then we migrate into Fortran 95 in starting 2.0, and now we are 2.2 now, and many models being input the sodium spent fuel pool models, and then high temperature gas model, and then sodium fine models here I'm going to talk about today. And then we have also implemented a number of non-LWR models, such as molten salt reactor, heat pipe reactors, etc. Um, and showing the version here. In the bottom of this slide here, showing, and also MELCOR is not just using reactor application, we can also use in fusion reactor. Folks in the Idaho National Lab developing a version of MELCOR that is particularly for fusion applications. And some of the phenomena they are looking at here is shown here. And then we also, like I said, we also looking at spent fuel pool. We study. We can look at the different batch, different uh, uh, history of the spent fuel batches in the pool. If there's an accident, what happened in them, how they release, and things like that. And we can do dry storage. Actually, see many of the spent fuel now is on the dry storage. And then we also, I guess, before saying that we have used MELCOR for long reactor facility application, especially at the DOE facility, and show some of the area, the site like Hanford site, Los Alamos, Savannah River, and Pantex that use MELCOR in one time or another. And basically looking at how much the release from the inside the facility out to the environment, because leak pack meaning how much the material fission product, not fission product, or radioactive material that released from inside the facility due to an accident like fire or spill, and then how they attenuate through the leak pad and out to the environment. That's a source term. Now, I said before, we have the high temperature gas reactor being developed in the early 2010 or so. So some of these improvements we have done in the past few years now, and we have some demo calculation showing in the last couple of years. And we model tricycle field failure, and then we have point kinetic as part of this time point here, and early 2000, part of 186 improvement in the laboratory development, research and development project. And then the sodium reactor that I'm going to talk about a little bit more here. Um, and then, of course, we're also looking at the excellent torrance fuel as well. And then here, on the right, showing the molten salt reactor we in process doing it. So let's talk about adding liquid metal properties in MELCOR. Sodium cooling in MELCOR, we implement the sodium equivalent state into MELCOR. Also including the sodium thermomechanical properties. The two models are implemented. Like I said before, the fusion folks in Idaho implementing their so-called fusion safety database based on the soft sphere EOS, and showing some of these liquid metals or material that being input using the software EOS, and it's a file. So all the property input as a files. And then we have the similar database, which is hardwired into MELCOR. So uh, the way we distinguish between a light water reactor is the file presence in the directory where you have your input files. So if you want to model the fly that using the software EOS, then you put a file called TPFFI. If you're simmer, you can put the simmer files in there. So that would distinct. But when you the simmer property is actually a dummy file. It's actually going to say to tell the code that we're going to use simmer properties. So we're going to using whatever the code has for simmer properties. So let's talk about the overall sodium chemistry models in MELCOR. This is like a little cartoon showing it's a pool type sodium fast reactors. It's like okay icon to me, but anyway, oops, sorry. Let's see. Here is the pool sodium, and then you have the cover gas. Of course, because they make sure it's inert. But if there's then they're doing an action, there's a air ingression there. There's chemistry, sodium chemistry can occur. So you can see some of these properties. I mean, some of the sodium byproducts are created during if there's air ingressions, and then you have vaporization, condensation, the aerosol processes occurring here. If there's a leak out into containment, now you have a more available oxygen and moisture in the containment that you can have reactions. The MS chemistry is showing here, showing the reactants like sodium, either the droplet form or a gas form, depends the state of the atmosphere, and then the oxygen, of course, and then the moisture in the air. So you can react when you're forming all the sodium byproducts, and then sodium hydroxide. And then of course when you react with water, then you can hydrogen produce. And then likewise, there's a pipe break in the containment that you have a drip of a sodium coming from the pipe break, and then you can form a spray, and then you have reactions there, and then if you drop on the floor, forming a pool, that a pool fire occurring, and so forth. And the blue showing it is some of this aerosol phenomena that we can model in MELCOR, like the fusion product deposition, leak plugging, because sodium is freezes is about 100 degrees C. So you can freeze in plugging some of this in the leakage path, and then you have gravitational settling because the aerosol getting bigger and it was settle. Okay. Here's the sodium models in MELCOR coming from Contain LMR. Contain also developed at Sandia in the 80s. There were two Contains in MELCOR. MELCOR survived, and Contain was dropped it from the NRC consideration. So consider as a legacy code. It's also developed here as NDA, I guess before. So there are a number of models in container MMR. It's a sodium fire, spray fire, and pool fire, as showing here. Those are being implemented. I'm going to explain a little bit more each of the model. And the atmospheric chemistry model is came from um, uh, contain code to develop that. Um, it- Mainly model, but it's only looking at just H2O as an ideal gas. We should explain a little later. And there's a two condensable model allow you currently, for example, a MELCOR only allow one condensable in a given problem. If you both water and sodium exist in the volume, only one of them should be condensable, so the UOS can be used. For example, for sodium reactor, of course, sodium would be condensable, and then H2O water would be treated as ideal gas. Now, the two condensable model is good because allow you in some instance that you have water instead of sodium that for condensable like a some high moisture area that you have a lot of water, then that's a condensate. So and sodium could in that case if sodium is much lesser amount in that volume, then you treat them as a ideal gas and so forth. And there's another model, the sodium concrete interactions, the SLAM model. It stands for SLAM, it stands for sodium limestone ablation model. And in the 80s, we do have had some number of experiments looking at sodium concrete interactions. And the SLAM model is came from the most experiments. And we did not implement it yet. Now, the debris-bred concrete cavity interaction, like the sodium reaction, the concrete, I mean, not concrete, the debris coming from the failure from the vessel down to the, this is more for loop type reactors. There's no interest for DOE. All these models that have been being implemented was funded by DOE Advanced Reactor Technology Program. Like I said, I'm going to a little bit more about the sodium fire chemistry model. This model is based on a NECCOM spray model from Brookhaven. Basically, is very easy, simple model. Considering the fall height, mean diameter of the droplet and the source, like the mass and its quantity, and using the internal droplet size distribution limit band from the Lekimia tanks Summa correlations, allow you to calculate the droplet size decreases as being consumed, the sodium being consumed. Only reaction of oxygens is shown here. One for uh, uh, monoxide, the other one for peroxide shown here. And it calculates some kind of ratio between peroxide and monoxide using this correlation here. And and the NAPCOM is only looking at just a downward spray. So we do have a variable direction, allow a spray going upward instead if the pressure on the pipe is a little higher. Um, so it's an enhancement from NAPCOM. And then the quantity tracking is showing here. We tracking the mass of the spray, the burned, and then anything that unreacted fall down into the pool to have pool fire interaction there, and then tracking amount the oxygen consumed and the sodium byproduct. Of course, the energy, the reaction that can be because exothermic reaction that add to the problem. Here in the 2000 timeframe, Sandia did have laboratory direct research development project a few years that conducting a sodium fire. Showing here the research facility is somewhere far away from my office here, but it's somewhere well, several 10 20 miles away. Is a research facility. Is like a cylinder like showing here it has a 99 cubic meter and it's a 3.6 meter in diameter and about 10 meter in height. And this particular test is in vessel. And the spray height is 5.3. Let me start the video here to show you. And while describing this this test, basically it's 5.3. Have a nozzle at H15 and 20 kilogram. The flow rate is 1 kilogram per second. It's pretty high. The particle size is a 3 to 5 millimeter. The initial temperature at this spray is at 500 degrees C, and then peak temperature measured at 1200, and the heat flux showing here is 89 equals 9, and then you can see it's a lot of reaction going on, the spray reacting, and you can see the growing. This is a black and white film, but showing you the magnitude of the reactions is tremendous. Let's see. You can see some of this cloud formation, things like that. So it's very it's enclosed. Everything in here. So the chamber is heating up as well. So the next model we talk about the pool fire chemistry model based on the Sol Fire 2 is an argon. Again, this reaction only considered is the oxygen. And of course, the important part of the pool fire is the ability for the oxygen from the atmosphere to diffuse to the pool area where you can react. So have a oxygen diffusion equation here is a function of temperature and pressure. The input parameter is basically there's 5 of them. Well, actually, yeah, 4 of them here. So is a fraction of oxygen consumed to form more oxide, and the fraction of reaction and heat to allow the heat instead of stay in the pool, part of it go into the atmosphere instead. And then 3 and 4 showing how much the peroxide stay in the pool if the peroxide forms. You know, so in theory, there's a let me show you the video probably better before I explain. Anyways, 4 is showing how much more oxide mass stay in the pool. If the difference is going to the atmosphere. And again, the tracking quantity is the mass of the sodium in the pool, and then burn one, and then how much oxygen being burned, and how much is, the sodium byproducts are produced, and then of course the energy of the reactions. In the same time frame, there's some pool fire tests at Sandia, but it's the outdoor fire because the problem is, we saw the spray fire, the intensity of the reaction, so they were safer to do it everything outside instead of inside of this facility. There's a number of tests being done. Let me show you this a slow motion picture of here is the sodium spray onto the drop onto the pool. I mean, into the pan. You can see it's quite quickly solidify because the temperature, outdoor you have lots of radiation, also plus the pan might be cool instead of heat up. So there's you can see that there's some reaction going on, some of the droplet coming up. Now this one here on the left is showing you a faster rate. You can see the smoke coming off, and then you can see the splashing going on. So you can see tremendous reactions occurring, pretty hot. So anyway, so they're showing you this the magnitude of the pool fire. If anything end up into there's some solidifying material being forming here. I can explain a little later here. Now, MSMA chemistry is not came from argon. About on the way it's developed. The model developed at the contain group folks. Here's considering the major 5 reactions. The first one is it reacted with the water, forming hydroxide, and then of course hydrogen created. And the second one also, but it's more in the vapor form. And 3 and 4 looking at just the similar to what the previous two model using reacting with the oxygens. Of A5 showing you some of the peroxide and dioxide, I mean monoxide can react with water, they're forming hydroxide. So showing here the react, and all the reaction assuming it occurs sequentially. So if there's an aerosol water that will be reacting, so this reaction occur first, so sequentially. Okay, and then we're looking at the gases. How's my time? Um, and then looking at the aerosol to aerosol reactions and the surfaces, or on the surfaces that they also can be reaction. So the atmospheric chemistry is kind of looking at anything other than spray fire and pool fire, and considering looking at also the formation of hydroxides. So pretty much cover everything else in the containment in terms of reactions. Okay. And here, of course, right now the models only work is when water vapor is ideal gas. Until we have the two condensable models implemented in MELCOR, then we can switch that around and looking at just the water as a condensable. Now, to encompass all this chemistry model, we created a so-called NAC package, so sodium chemistry. So all this chemistry model are including in that package. As you know, in MELCOR we have many different packages. CVH package, you have um, RN package. So this is one of the package, but it's only deal with sodium chemistry. We're showing some of the data structure classes we added, sodium, water, aerosol, and hydroxide, peroxide, and monoxide. And then we did a lot number of things in validate the model. APCO AB5 is the upward spray experiments done by Hanford Engineering Development Laboratory in the 80s, I believe. AB1 is a pool test, and then of course we compare it to contain LMR results since we implemented the model from them from the contain LMR. And then here, we're looking at the improvement of the pool fire. So like I said, we can using user input to explore the responses without code modification. So we can do it explicitly in the input to see if the model works before we actually hardwire into the code. Because when you put in the code, there's a number of things you have to do to make sure that vigorous testing, development testing, and make sure okay. So this way we can test the model whether or not it really is what we want to do, and then we implement hardwire into the code. The Corium spring models in the LWR is done that way. We did it in a control function first, then before it looks okay, then we implemented the mobile. There's a reason why you want to hardwire in the code, because some of the property you don't have to include it in your input. You basically use really properties in the MELCOR already, so a lot easier, faster. Now we're going to talk about the cooperation with the JAE under the CNWG now. The collaboration with the JAE on sodium 5 research continues in several years already. And we're looking at the computer code development exchange to benefit both code development in Sandia and also in JAE. And in 2 years, JAE sent a staff to Sandia here to station here for a year to use MELCOR and interface with the MELCOR development teams to see how he interact with looking at sodium fire research. We hope they continue the research collaboration beyond 2021. Now, at least we do have one sodium fire expert meeting exchange in the fall usually in Sandia. So the JAE folks will come to Sandia for the meeting, and then in the summer in one occasion, we do go out to Japan to have a meeting there too. In FY20, and Mr. Hiro is working here before the COVID occurred. So he was looking at the sodium pool model enhancement with us here at Sandia. And now we just have to do virtually meeting, virtually, you know, running calculation here and exchange ideas on the collaboration. And the code comparison, we include the sprints and the spectra, both of JEA codes. And then like I said, we're going to do experimental data exchange. And now we're more looking into aerosol transport, which is important for Sotra. And then hopefully, the COVID um, completely gone, that hopefully JAE will send some staff later 2022. Each year we do at least one joint conference paper between Sandia and JAE, and then we do have a progress report every year about this time to send it to DOE and then another stakeholder for the collaborative research work. Now, code-to-code comparisons, looking at mainly on the sodium fire modeling currently. We want to look at beyond what is provided in the container bar. So like I say, JE code is a sprint and spectra. Sprint is the lump parameter code for sodium fire analysis. I believe Mr. Hiro have given a seminar to you guys maybe early last month, a couple months ago. And Spectra is the new code. The integrated sodium fast reactors related code is being developing now. Like I said, we try to improve both code at both institutions. And then I'm gonna talk about the enhancement on the pool fire, mainly on the pool spreading, and then the how do we improve the reaction rate if there's an oxide layer buildup. So we talk about enhancement now. So in FY20, we're adding a spray fire model. We're looking at the 1D heat structure limitation in MELCOR for heat structure, implementing the quasi two-dimensional heat transfer model, and then how the oxide can affect the oxygen diffusion coefficient, and to improve the pool fire reaction rate modeling to better equate to the experiments. Let's talk about the liquid sodium spray model, spreading model. I saw the video. The spreading may occur early, and then you can see it in slowly in this stop in one of the videos. So spreading may be important, especially the release rate is low. So anyway, here is just showing the current models that we implementing. The 1D radial spring model is like a pancake model to my opinion. It came from the cavity package in MELCOR, showing is a viscous dependent model. Showing here is a viscous term versus the gravitational force, and you can write that as function the radius as function time. You can see this the equation become from here to there, and then you solve this equation, you come up with this um, uh, final equation, a function T per delta T. It has a quantity, is function of viscosity, is function of the mass of the sodium, and then the density of the sodium in the time step, and then some constant coefficients. And then because of the viscosity can be affected by how much solids in there. So we're using the Riccati correlation, showing here this expression here. Epsilon is a solid fraction. The higher the solid fraction, the higher the multiplier would be to the viscosity. To implement this model, we can put it into CVH, the pool model, the pool section of the CVH. Here is the new record that input record CVP diameter is a diameter record that allow you to model the functional amount of sodium liquid in the problem. It was starting spreading. So it's a control function. Use control function to model R sub t. Here is a expression on expressing in the control function, display R45, and here's the equation showing here, and how which actually there's nice thing about control function. We have a formula control function that you can actually model the whole entire equation, right hand side equation into here, showing here. Uh, so it's pretty easy to do. And here, of course, this is a previous value. So when you call itself is using the calling the previous value. So that's how you're incrementing your R. The smaller the CR, C1 here, the smaller the spreading is, right? So if you have a higher viscosity, also slower the spreading, okay? Smaller mass, as time goes on, most of the solid, I mean, the liquid sodium going to be reacted, so you have a smaller mass as well. The next one is the pool heat transfer models. Time. Okay. Like I say, the recurrent model, MELCOR is 1D model. Basically, it's a um, the catch pan is a uh, one node, then in the sodium pool. So excess heat loss from the so you under I guess over predicting the temperature loss from the pool. Now in the actual experiment, the temperature underneath the pool should be higher than the outside the pool. So showing here. So small heat loss from the heat swimming pool. Okay. In reality, this should be this, but currently we are implementing a 2D heat structure model. Cartesian models is working, and cylindrical model is being implemented and testing right now. Here's the in the meantime to uh, to address the limitation of the 1D models, we're using a 2D 1D heat structure model showing here. Heat is allowed through, oops, sorry, through the below the pool, and then no radial conduction and no heat going through outside the pool. And the equation is showing here, TP dash one is the underneath the pool, and showing here this equation. You can derive it, and this is the heat power then being times the equal to the heat transfer coefficient times this quantity temperature times the pool. So it's in watts. So you can derive this, you can calculate what is the temperature that P pen dash one is showing here in this equation. So you can translate in the control functions. The first set is looking at the heat transfer uh, um, between the pool and then the hatchband. Showing here this equation, this control function, 76. And then the temperature below the pool is shown here in this control function. Okay. Now the pool oxide layer is important. The limiting the oxide being, imagine showing here this oxide crust here. In the experiment done by Sandier in early 2010, they shown that this oxide layer built up above the pool. This is showing here is 1D, and then sodium pool, and then you have the substrate pad, the catch pad. It's a 1D model. And you can show the temperature down in the graph here. The lowest temperature, of course, is the catch pan, and then you have rising in the pool, and then you have where the reaction occur in the interface in the pool and in the crest, because the high oxygen had to come from here and penetrate the oxide to go through to interact with the sodium. And zero mass fraction of oxygen showing here at the interface where the pool is, and then you can see the increase in, and then of course the ambient mass fraction of oxygen. Okay. Okay, the first set, the equation is the current model. Basically, the diffusion of the oxygen is equal to this expression, a function of temperature and pressure. Okay, the improvement that we included here is incorporating the oxide layer buildup and showing the this three equation equivalent to that. So the difference between these two here, there's the red and then the black is the addition of the oxide layer. And the oxide layer delta is the amount of the oxide in the pool is have some kind of porosity. Um, in the observation of the experiment, they shown that they see a lot of porosity in the crust. So porosity makes it swell up. So we're going to model this this equation as well as this equation. Before that, let me show you the typical input for invoking sodium chemistry. Here's the required input is NAC input, and then you tell them what RN class you have. In this particular calculation simulation, that we're going to have model the spray because it's some drops and it takes a while to get to the become forming a pool. So we model the sodium spray as well, and then the sodium pool fire model is shown here. And here is where you putting the control function for the diffusion of oxygen too, and the rest of them are still a constant. Okay. Here is the oxygen diffusion control function, and then you have other control function. This one showing you how this equation being modeled into the control function, pretty close to what you have in the mathematical expressions. And this is showing you how to calculate the gas diffusion, which is showing you the default one here, the DABO. So so all this is going to contribute to that, and then additional control functions added, especially because we don't look at uh, the oxide layer thickness because it's important for the equations. So showing here is a function of the mass and then peroxide and then the monoxide and peroxide, and then also the porosity. We assume some of the porosity shape look like is a function of solid fractions based on this based on the solid fraction shown here, which account for how much sodium mass byproducts in the pool. So we can calculate that and then plug it into the diffusion oxygen diffusion equations, and then give you the results. Now talking about benchmark. Oh, I have 5 minutes. Okay, here's the experiment, the F71 from JAEA. Basically, it's the 3 cubic meter diameter cubic chamber called FAB. Basically, your air coming in the same rate as going out to the top here. Sodium coming from the top and spray onto the the drop height is about 0.1 meter to a form of a pool, a catch pan here. And the measurement of beside thermocouples and temperature, you have aerosol sample through and gas sample through the location of the vessel and the X ducting. And then here's the temperature. The temperature is sodium about 500, equivalent to the spray fire the video that I show you is a column, and then drop height is showing here. It stop about about 25 minutes or so, and then the rate is very small in grams instead of a kilogram, and then total leakage is about 5 kg, and you have quite a bit relative humidity there. The vent rate is about 3 cubic meter per minute. So 1 minute, all this air volume will be exhaust to the ducting. Here is the post um, um, solidified pool methodology, showing the final states of the pool sample here, and then here's showing some a description of what the layers look like. It's showing that the middle section has a porous layer, and then and it actually swell up quite a bit. And then here the middle section was a little lower, and on the right showing some measurement of different sodium byproducts and sodium byproduct and so forth, showing here some, what we're trying to get out here is some of the sodium hydroxide is near the surfaces, near the top, uh, and then sodium is the inside. If you some of the red symbol is a sodium near the center of this sample here. So what I'm trying to say, the sodium hydroxide may be coming from the reaction in the atmosphere, and that's all onto the top of the, it could be the top on the sample here. And then on the right, on the left here, showing is a concentrated sodium versus time, showing you in the beginning is pretty high, and then at the end is very low. So there's a drop off, quick drop off. It is a log scale. Here's the MELCOR models. Basically, it's a three control volume. Fab is where the reactions occur. And then here's the heat structure in the MELCOR models. And then, like I said, the sodium fire and pool fire model was activated. Here's some result comparison. The base case just using a default contain models, which is the dot and red line, and then everything that we talk about, the three modifications is a combination. So you can see that the temperature of the base case is very high, but the combination case is getting close to the experiment, but the catchment. So, but this is a 2D quasi model. So, some of this information, some of the heat may not be transferred into the pan correctly, and some improvement may be needed there. Here, showing you the gas temperature between the experiment and then the MELCOR runs. You can see the combination is getting closer to the experiment. So code-to-code comparison. Here showing a pool spreading model. Showing spread is using this blue curve here, and then the experiment data is the symbols, and the MELCOR base case is this, and then this spreading model that we implemented is this one. So if I enlarge, and then the coefficient we use is showing it here. So if by and large, you can see it's very close to comparable to the experiment as well as the other code. Here's the comparison between the Sprint and MELCOR, and then the experiment, showing the pool temperature very close, and then showing catch pan, of course, a little underpredicted, and then you have the gas temperature, and then the reaction rate here. You can see the reaction in the experiment were high in the beginning. There's where the stop discharging is about 25 minutes. You can see, and then quickly drop off. I guess this is because due to the oxide buildup. And both code are not predicting that well in this particular simulations. In conclusion, it's basically saying that we demonstrate that the MELCOR can model model the sodium discharge phase under predicting, and then after the discharge phase, MELCOR over predicting for this particular instance here. Important agreement between the experiment and then and the exploratory control function model that we just mentioned here, which is good. The sprint results are a good agreement in MELCOR for the benchmark models. Something I want to throw to you this year, that we are looking at the aerosol physics. So we are looking at implementing a dish beside the diffusion oxygen. So we're looking at the amount of sodium byproducts that can be, say in the pool. Like you can see this experiment showing that at the beginning there is quite a bit um, uh, released into the atmosphere, the chamber. The reason is at that point the oxide layer doesn't build up, so most of the release from the pool should be just going to the atmosphere. As an oxide layer build up, they limit the amount of sodium byproduct going to the atmosphere. That's why it drops significantly. We are getting closer, but not there yet. But we are working on that and see if we can improve the results to explain what happened here. And here's the end. I think I'm on time. Any question that you have?
Okay, thanks a lot for a very impressive presentation. So I will let the audience ask questions first.
So I have a question. Can you hear me?
Yeah, I can hear you.
Great. Yeah, so I was interested in some of the atmospheric chemistry modeling part. I mean, you mentioned, I think it was back on slide 14, that you do this in sequentially, but then you had a bunch
Yeah,
of
because how the reason is it's a lot easier to model that way. Well, it came from continuing MMR, so we didn't. Maybe we had to explore. The reason is, I think that there's a reason why this reactions occur because at lower temperature. Some will require higher temperature when you're in vapor form. So I would say that that reaction occur first at the in a lower temperature.
So you
If you
mean
look at
sequentially in
sequentially, mean if there's sodium aerosol and there's a sodium, water aerosol, this reaction go first. Because you have the competing effect from sodium for all the other reactions. So you had you're not solving all 5 equations simultaneously. That's requires some calculation logics, which is
Yeah, I guess
it's
that's
not
kind of
that
my
hard to do,
question.
but it just for this one we just we just got it from the implemented from the contain LMR. So in the future we might change that. Depends on more, because like I said, that we don't have any experimental data to look at all this, because we're looking at this outside the pool fire and outside spray fire. So we don't not sure because there's no how you say experiment showing how the aerosol behave if we have a sodium aerosol and you have a water aerosol. I think it would be nice to have this experiment that's showing that when you two combine, are they how they affect the reactions, things like that. So all this is capture anything exclude from those two other chemistry fire model. We
Well,
try to
just so I understand, and I guess
yes.
was my question, maybe what I didn't see properly at the first
Sure,
time
go
was
ahead.
the difference between the aerosol and the gas phase. So it just occurred to me that equation A1 would consume all of the reactants, and then there'd be nothing left for the following equations. But I suppose because they're different phases, you have the aerosol phase and the gas phase. Maybe that's why.
Yeah, there's different phases.
Okay. I
Yeah,
understand
so
now.
yeah,
Sure.
there's a difference. Yes. Thank you.
Got it.
Thank you.
And a related question then, when you model the space, I mean, MELCOR uses a nodalization, so there's obviously a lot of transport happening in the atmosphere.
Yeah,
Right?
there's a lot of things going on in the atmosphere. Yes, it is.
So how do you
You're right.
model, how do you nodalize the atmospheric space so that you get the right mix of chemistry and mass transfer and things like that?
Okay. So we execute by sequentially by each package. So we pass information from like CVH to RN, for example, or the NEC software. I mean NEC package, for example. So we get information either from previous time step or current time step from CVH, and how much sodium in gas phase, or and then we're gonna then we're gonna calculate what the reaction would be. Similarly for the RNs, so we're going to know from the current time step or previous time step that is what is the sodium aerosol going to be if they forming aerosol, and then how do we react with them. So that's how we do by each package is interface, but there's a sequential order in MELCOR.
Sure. I mean, I think my question is a little different, is what's the fidelity with which you nodalize the atmosphere?
Atmosphere is a single volume.
Okay.
It's a lump parameter.
Okay.
So yeah, one temperature. It's not like not a CFD code. So so I understand you correctly.
Yeah, I knew it wasn't CFD, but I just was wondering if you use some nodalization that was somehow.
No, there's no nodalization. No, there isn't. No, the lump parameter is only one temperatures.
Understood. Thanks.
Yeah, sure, no problem. Any other questions?
Nothing in the room here. Anybody online?
Yeah, I can ask one question.
Sure.
So when you are considering a fire model in a containment, did you consider combustion process?
Combustion process?
Yes.
Like what kind of combustion? They all, can you explain a little bit more? What do you mean by that?
Oh, so combustion is something like a stronger fire that might happen in a super short time. Okay, so let me ask in a different way. So now we know that MELCOR can calculate the fire mode of sodium in containment. And there might also be some other softwares like Flight 3D and also Converge CFD and FDS. Do you have a comparison of these softwares, the different models in these different codes?
No, we only looking at for this particular study, we don't looking at how to improve the model. In the future, we might want to compare the other code out there. Right now, we compare to JE Sprint codes and maybe maybe Spectra in the future, but we hasn't compared the other code. Most of the code that we're looking at is the non-parameter codes. We hasn't looked at the other codes out there, not yet anyway. It'd be nice that we can compare the other kind of codes so we can see how well we do in MELCOR.
Okay, yeah, sure, sounds good. Seems
yeah,
like
I mean that's right now we're just looking at how do we improve the model that we can closely match equate to the experimental data, and then make whether or not those make sense. And like oxide layer buildup is important for oxygen diffusion. It is. So, sounds like it will be. And then how they affect the sodium aerosol suspended in the air. It does, because you have less if you have oxide build up in the pool surfaces, it's harder for the oxygen to come in, and harder for the air the byproduct to go through the oxide they're going up to the atmosphere, right? So you can see the decrease. So those are important phenomena that we want to track. The reason we, like I said before, I didn't explain, but sodium does carry some fission products into an reaction, and so any release from the sodium reaction that could be also ultimately released other fission products in the air, I mean the atmosphere, right? So, and also sodium is also activated too, so activated materials. So
okay, thanks.
no problem. Anything else?
So if there's not other questions, and I have a small one, a quick one. So where you edit your model? Did you edit your model in a notepad, something like notepad, or you are using Snap to build your model?
You mean how do we build the control function?
Build everything, build control volumes, control functions.
Oh, you can do it in the Snap if you want. We just do it old-fashioned way, just open the files and
so where
adding
you
just adding, changing the because it's not complicated. It's only 3 control volumes, so it's not for this particular instance. You have very small.
Okay, so you're using Notepad.
Yeah, no, I don't use Notepad. I just use and then run this simple problem. It's just not like this particular instance is only 3 control volume here, and there's a time there's 2, the environment and the pre-environments are both time independent volumes. The only one that you're looking at the flap. Now eventually, if you're looking at this methodology, this right here, want to know the spatial solving of the fission product, I mean the byproduct, we might have to break the control volume into smaller sections, so allowing you looking at the distribution. That's a little more complicated, but to match, if we want to see something like that, to show, because this is showing a spatial distribution of the byproducts. This is a little slightly difficulty, but there's a way to do it, but it's it's more complicated because we want to see right now we can see some of these byproducts in the edge or at the center and or middle section things like that. So it requires some effort to model this control volume instead of single volume into multiple volume.
Okay, sounds good.
Okay.
Okay.
Good.
If we don't have other questions, let's thanks Dr. Louie again for the presentation.
Thank you for inviting me. Anybody have any question? Mr. Hero, you have anything to add? Since you've got.
Yeah, it's okay. Thank you for
It's okay.
the presentation. Yeah.
Yeah, appreciate to inviting me to the seminar. So hopefully you guys use more MELCOR. And let us know if you want to do something like this. If you want to plan to do some experiments, that'd be nice. Especially the atmospheric chemistry model that we there's no existing model that can test this when we actually implement. It's difficult to looking at the if there's a sodium condensed sodium that's right on the wall, vertical wall, and then has a reaction going on. How do you model that? So it'd be nice. It's challenging for model this atmospheric chemistry due to a condensate, sodium condensate on the heat structure. So vice versa, if there's a water condensate on the wall, and then you have sodium gas that gonna interact with the sodium, how do you do that? So those kind of things that it'll be atmospheric chemistry model will be there to look at, but without additional experiments, so we can't really check this model well. Per se, like I say, the aerosol interaction, maybe we need some kind of experiments to do that too as well.
Yeah.
Okay.
Okay, great.
Great.
Thank you.
Thank you much.
Bye.
Bye bye.